Right, so recording started. Yeah, I think if it's all right, I'm just gonna start now. So hello everyone, my name is Jan Behrens, and I'm happy to present the today's lecture for the topics of current research and the TCM group. And I'm going to talk about topological semimetals and their connection to high energy physics. And the idea is that I'm going to give 3 lectures on this topic. So the first one is obviously today. Then the next one will be on Wednesday at 10 in the morning. And the third one is on next week, on Monday. And today I'm going to give a short introduction to topological insulators and semimetals. And of course, this is quite a vast topic. So it's like only a very short and brief introduction. So I hope you don't expect me to go into detail with this, but on the other hand, I'm trying to highlight some aspects that might be important for the other parts of the lectures. So on Wednesday, I'm going to talk about quantum field theory descriptions of similar phenomena. And in the third lecture, I hope I have some time to go into more interesting stuff, especially to anomalies, which I'm also going to briefly mention today, and some ambiguities with the field theory description and how to resolve those ambiguities on a lattice. Like large parts, this lecture is, in large parts of this lecture is based on notes by Adolf Groshin. So he prepared these notes during a summer school in Donostia, San Sebastian in 2017, and they are also published. And I completely forgot to post the references. So I hope I'm going to do this at the very end of the lecture, or maybe on Wednesday's lecture, because I completely forgot to look for the links. So you don't have to copy it and copy all of this. So I'm definitely going to provide links for all these references at some point in the future. And other useful references, especially if you have a condensed matter background, then some of the high energy theory literature might be interesting for you. For example, like this book by Bettelman and another one by Fujikawa and Suzuki. And there are, of course, loads of review papers about topologic phases, topologic semimetals. And during today's lecture, I'm I would recommend some other reads, especially 2 papers by Nielsen and Nemiya, and many other others, including these Groshin and Landsteiner references about topological, about wild semimetals especially, and their connection to high energy physics. So to start with topological phases, I'm going to introduce the quantum Hall effect first, because this is the most basic example in some sense for a topologic phase, but this already sets the stage quite nicely for today's lecture. So the idea is that you have a 2-dimensional sample and you apply strong magnetic fields orthogonal to this 2-dimensional sample. So here on the x-axis, you can see that the magnetic field has strength around several Teslas. So it's definitely a quite strong field. And if you measure the resistivity of these samples, then you realize that the XX resistivity is 0 for most of for the biggest ranges of the magnetic field, whereas the XY resistivity, there are some plateaus in the resistivity, and it turns out that they are quite nicely quantized. So the quantization is up to 10 to the minus 9. It's very exact, and it's independent of local details, meaning that you generally have disordered samples, of course, and the quantization is completely independent of the disorder, up to certain strengths, of course, but generally for small disorder, it doesn't matter if you have anything in the sample. And what's also quite important to highlight is that if you have such a plateau, the XX resistivity and accordingly also the conductivity is 0, which means it is a gap phase. And then you have some peaks in the resistivity whenever the quantization of this plateau changes its value. So what does it mean? So we're looking here at a non-interacting phase. That's quite important. And I'm also only going to talk about non-interacting phases during today's lecture and also during the next 2 lectures. This phase breaks time reversal symmetry, which is also quite important because we have a magnetic field, and the magnetic field breaks the time reversal symmetry. And the quantized, the Hall conductance is always quantized whenever the longitudinal conductance is 0. So whenever we are in an insulating phase. And the jumps in the longitudinal resistivity, sorry, whenever the Hall conductance jumps, we have like a non-zero longitudinal resistivity. So what does it mean? So it means we have, if we tune the magnetic field, we go from one gapped phase to the other. And these gapped phases are characterized by a quantized Hall conductance. And whenever this value changes, we are effectively in a metallic phase, in a non-gapped phase, which means that we have several gap phases separated that are somehow distinguished by like some kind of invariant, some topological invariant, or topological response so far. These are separated by gap closings, these phases. And here I'd also like to mention that here I'm considering a non-detecting phase, of course, but interaction effects are important for larger fields and for lower temperatures, as it was discovered soon after the original discovery of the quantum Hall effect. But I'm not going to talk about this in detail in this lecture. So how can we understand this quantum Hall effect? So quite a hand-waving, but also intuitive explanation goes like the following. So if we have like this magnetic field indicated by these gray circles that pierces into the 2-dimensional samples, then we get like some semi-classical orbits of the electrons in the sample, which are circles, or charge carriers in the sample to be more precise, which are circles. And in the bulk, this means we have like a lot of counter-propagating modes, which will generally gap out. But in the surface, they don't gap out. So we have like these kind of axis modes at the upper and lower surface here. And I'd like to highlight that this is like a single propagation direction. So it's either left moving or right moving. We don't have backscattering. So generally you would expect that, it's a gapless phase, and you don't have, there's no way to open up a gap in the system. So the bulk itself is gapped because of these counter-propagating modes, whereas the surface is gapless. And as a result, we get a quantized Hall conductivity, and it's quantized because of this n, which is an integer, and the n simply counts the number of boundary modes. So this somehow explains where this effect comes from, and also somehow explains why it is quantized, because the number of boundary modes is necessarily an integer, and so we also expect that the quantized Hall conductivity is an integer. But I hope I am able to describe it in more detail later, why it is exactly quantized. But we can also relate it to like a topological quantity. So it was first discovered by Thouless and others that this is related. We can compute it via the Kubo formula and get like this n as a TKKN invariant, and named after the authors of the famous paper. Or it's also called the first Chern number that characterizes the bulk of the system. But before going into detail how these edge modes or boundary modes are related to the Hall conductivity, I will first go to another example, like another system that exhibits such a quantized Hall conductivity. And I'd like to point out that the other example doesn't require a magnetic field, and it's a pure lattice realization, and that's the so-called Haldane model, which are just like a tight binding model on a honeycomb lattice. And we have a nearest neighbor hopping that is real, but on top of the nearest neighbor hopping, we have a complex next nearest neighbor hopping. So whenever we hop from this light gray to other light gray unit cell atomic positions in the sample, we acquire a phase, and the arrows here indicate like which direction gives a positive phase, because like the model is emission. So if we hop into one direction, we acquire a positive phase, and if we hop into the other direction, we acquire a negative phase. And on top of that, we also would like to have a sublattice potential, which means that like different from graphene, for example, where all the different units, all the different atoms are describing the same carbon atoms. Here we would like to have like a model where the two sublattices, like here indicated in some different shades of gray, have different chemical potential, which breaks the sublattice symmetry of the model. And the complex hopping breaks time versus symmetry. But although time versus symmetry is broken, similar to the quantum Hall effect, we don't enclose a net flux. So what does it mean? So if we think about like the whole lattice of these honeycomb unit cells, we can think about like hopping just for like round a unit cell. And during this hopping process, we always acquire phases. And as you can see by the direction of the arrows, like the different phases always cancel out. So if we would acquire a phase, this would mean that we enclose a magnetic flux. So that would be effectively a magnetic field in the sample. But since we don't acquire a phase, we have no flux inclusion, so hence no magnetic field. And very similar to the quantum Hall effect, in these systems, we have some boundary modes. These are counter-propagating. So if we would plot the band structure for this cylinder geometry that I'm plotting here, we would see the following. So now we have periodic boundary directions along one of the lattice unit vectors, which I call A1. Such that we can plot the spectrum as a function of the momentum along this direction. And here the color code indicates the localization of these boundary modes. So all the gray modes are in the bulk, whereas the blue and the red modes are localized on the different surfaces of the system. So actually, I'm a little bit colorblind, so for me it's very hard to distinguish these two modes. But I hope you can easily distinguish those. And this only occurs for certain regimes of the parameter range. So we now have like two different tuning parameters. We have like this complex hopping with a phase phi. And we have the sublattice potential, which is called capital M here. And here the different phases indicate like the different Chern numbers. So we have either 0, +1, or -1 Chern number. +1 or -1 distinguishes like the propagation direction of the boundary modes. So remember, like they're always counter-propagating on the different surfaces, but of course on the upper and the cylinder geometry surface, that can be propagating to the left or to the right, and these are distinguished by the signs of the Chern number. And like similar to the quantum Hall effect, where we also had like the different phases distinguished, like separated by gap closings, here it's the same. So everywhere where you see the line separating the different phases, the gap of the model closes. So how are these surface states, how are they related to this quantized Hall conductance, which I wanted to go to? That's probably the best to explain if we consider like a slightly different geometry, like a slab geometry, which is simply for sake of the argument, it's infinite in one direction and it's finite in the other direction. What I can do now is that I only consider the two surfaces separately. So I can consider the blue states, so to say, like only the lower surface, like the bottom surface of this model. And I can consider the red states, so only the top surface of the model. And I'm sorry for for the gap in this model. So this is only because of the numerics I did. So this is only like an artifact of separation of the two models. So of the two modes. So like don't pay attention to this gap here. So what I want to do now is to think, like to consider what will happen if we apply an electric field on top of this model. And I'd also like to point out like an interesting connection to David Tong's lecture. Those of you who have been to the CPGM last week, they will certainly remember that these two theories I'm plotting here are chiral theories, so they can't be realized on a lattice, mostly because of charge conservation. But of course, it's still possible to have like a higher dimensional system where these chiral theories are occurring at boundaries between different phases. So here it's like the boundary between a Chern insulator phase and the vacuum. But of course, you can also think about other boundaries where you have effectively some chiral theories realized in a higher dimensional system. So just like another reference to the CPGM, so we might actually live in a big quantum simulation, but like only on the surface of a higher dimensional quantum simulation. So if we now think about what had happened with a electric field, we consider a certain occupation of these boundary modes. So here I just included like the dashed line as a chemic potential, and these dots indicate states that are occupied for this specific value of the chemic potential. If I now apply an electric field on top of that, then since like all the different occupied states have a certain group velocity, I expect that they move accordingly to their group velocity, so that we have like the chemic potential in some sense goes down on one of the two surfaces and increases its value on the other surface. And now we need to counter this change of the chemical potential, because we like to be in equilibrium, of course. So what effectively happens is that we get a current that is the effect of the change of the chemical potential of the boundary states. So to ensure charge conservation, a current must flow from one surface to the other surface. And this change of the occupation is like a response to the external electric field, and it's a result of current conservation and flows orthogonal to the applied field. And importantly, it flows through the bulk states. So it's like the bulk states away from the Fermi energy that are contributing now to this current, and therefore contributing to the quantized Hall conductance. Another way to think about these boundary states is if we start directly from a continuum theory. So we can think about like a two-dimensional continuum model where I have like a gap model. So whenever this value m is constant and positive or negative, doesn't really matter, we get like a gap theory. But here I want to have a varying m such that it goes through 0. So I'm thinking about this situation where, as a function of x, m changes from a certain negative value minus m naught to a certain positive value, which I plotted here as plus m naught, but it doesn't have to be symmetric. So it doesn't need to be minus m naught and plus m naught, can be two different values as well. It doesn't really matter here, but it's most important, like most importantly, I would like to have some kind of shape of these m that goes through 0 and changes from a negative to a positive value. And if I have such a situation, then I can find boundary solutions for this problem. So this capital psi is now my ansatz for this problem. And if I solve the Hamiltonian, like with this ansatz, it's quite simple actually. I realize that the energies are simply ky. So if I would plot the spectrum of the whole system, then I would get, like in gray, the bulk modes for the two constant values of minus m naught and plus m naught. And then in black, I get this linearly dispersing boundary mode with energy simply given by ky. I can do the same for the opposite situation, where I change this m naught from a positive to a negative value. And the boundary solutions must now have like a different sign, simply that that they're still like nicely localized at the boundary. So so it's now simply the exponent of plus the mass term integrated over position. And this changes the energies of the solution. So we have now the solution psi prime with energies minus ky. So if I plot the spectrum here, it looks very similar. So the bike states have exactly the same energies, because it's like still two bikes with the same values. But now I get like boundary solutions that propagate in the opposite direction and have like a opposite energy minus ky. So this like kind of an explanation how these boundary states emerge from a continuum theory. But if we go back to a lattice, then I would also like to introduce some other quantities that are related to the winding of the eigenstates, and might convince you a little bit better how this is like a topological thing that we see here. And in order to do that, I'd like to consider the evolution of a general state. So I just have like some general wave packet phi, and I expand it in terms of my energy eigenstates psi n, and everything is time dependent here. So I have like a time dependent Hamiltonian. Therefore, my eigenstates are also time dependent, and they're instantaneous eigenstates, which means that at each time they are solutions for the solutions of the Hamiltonian, giving as well time dependent energies. And if I would now I'd like to see how this general state phi evolves under the Hamiltonian. This is like then the like I want to go to something else, to the adiabatic evolution of the problem. So we start by just simply considering the time evolution of the problem, and get like a different form of the Schrödinger equation, which includes the states phi itself and the derivative of the coefficients plus derivatives of the state phi, which I can solve by simply multiplying the bracket from the left. And I get like an equation for the different coefficients Cn of my expansion. And what I can see quite easily here is that, first of all, the first coefficient that is proportional to the Cn itself is purely real, which means that since I have like minus I times something purely real, it will only give a phase in the time evolution of the problem. The second part here, I can rewrite it, and you can maybe do it as an exercise if you're not familiar with this. I can rewrite it as the quotient of like the time derivative of the Hamiltonian sandwiched between eigenstates, and the energy difference between two eigenstates. So whenever I have bands that are separated in energy, and I have a Hamiltonian that sufficiently slowly varies in time, these coefficients become quite small, and I can simply neglect them. So this is like the gist of the adiabatic theorem, that if I evolve a system sufficiently slowly in time, I only need to consider the time evolution of each band individually and can completely neglect the coupling between the different bands. And yeah, as a solution of this problem, I get like this kind of adiabatic evolution where we have a phase that includes both like the contribution from the energy evolution of the system, plus like this phase factor related to the time time derivative of the eigenstates. And it's called geometric phase because it only depends on the geometry of the problem. So let's say I have an Hamiltonian that parametrically depends on time. So I have h of t that depends like that I simply write as h of some capital R, some parameter that in turn depends on time t. Like in this case, I can rewrite this integral over time of the phase. I can rewrite this as an integral over the path. So I have like this parameter r that evolves somehow in time, as indicated by this blue line here, and along a path gamma. And the evolution itself of this phase doesn't depend on like certain time on the time itself, but only on the path gamma itself and how r evolves, how the eigenstates evolve along this path r. But generally, like, and for a long time, this was like not considered as something important because like for a long time, people have realized, okay, like this second term, this geometric phase is generally gauge dependent. So that's quite easy to see. So if we change our eigenstates using like a different gauge choice, then we can also change the resulting phase, so the time, like the product of the bra and cat of the r-dependent eigenstates, and so like the whole quantity is a little bit ill-defined and gauge dependent, and we can always choose it such that it's zero. So this is called parallel transport. And it's commonly done if you look at any papers considering time evolutions of the system, like this is quite a convenient gauge choice that people will use, that you use the parallel transport gauge and you can completely neglect this evolution of this geometric phase here. But this is not always true, because this is only true if we don't have a closed path. So if we have a cyclic evolution of the system, and then our path gamma set changes such that it is a closed path, and it's still gauge dependent because the gauge phase can still like a different times t and t plus capital T, which is now the periodicity of my problem. It can still change by 2 pi. So this resulting Berry phase or geometric phase can only change by 2 pi n, but it's definitely defined up to this 2 pi n. So if we have a closed path, then this Berry phase will generally contribute to the evolution of the system. And this was just like a historical remark. This was realized quite late in quotation marks. So here I put the reference to Berry's paper from '84, although people of course considered adiabatic evolution as early as in the late 1920s or early 1930s, but like only more than 50 years later, it was realized that although you can always gauge it away for open paths, it holds relevant for closed paths. And it turns out that its relevance is quite significant, especially if we think about a lattice system. So like, okay, it's quite nice, right? So how, so what does it mean that for lattice systems that we need to consider closed paths of the evolution of some parameter? And an obvious choice is in some sense that we consider our crystal momentum K as a parameter that we vary in time. For example, if we have, let's here just to be a bit more concrete, we have a 2-dimensional system and apply an electric field along the x direction of the system. So what it does is that if you consider the semi-classical motion of quasiparticles, then you realize that there's change in momentum is proportional to the applied electric field. So each, like if we consider quasi-particles with an applied electric field, it will move in momentum space through the whole Brillouin zone. And since like the momenta 0 and 2 pi are identical, the quasi-particle will move along a closed path in the system. And these one-dimensional closed paths are very much related to like a very related quantity that's sometimes called the Zeg phase, which gives you the response of the polarization. So the Zeg phase, like the evolution of an electron, if we apply an electric field, gives you the polarization along a certain direction of the system. Another closed path is, of course, like a magnetic field, so similar to the quantum Hall effect, where we already saw like this orbits and real space. We similarly have similar orbits that are not necessarily circles, but sometimes circles in momentum space, such that this would be like a different example for a closed path. And if we look at the semi-classical equations of motions themselves, we also realize that the Berry phase or Berry curvature affects the motions of electrons. So the velocity of quasi-particles is not only given by the group velocity, which is the energy derivative, but on top of that, we have a second term that is proportional to the cross product of k dot with omega. And this omega is usually called a Berry curvature, which is the curl of the Berry connection, and the Berry connection is now the equivalent of this property that went into the geometric phase, the connection that contributed to the geometric phase, only with a very subtle but sometimes important difference that we now consider the functions u, which are the lattice periodic part of the Bloch eigenfunctions. Usually doesn't make a difference, but sometimes like there's a subtle difference if we consider u of psi here. And using the Berry curvature, we can again compute our favorite quantity, the Chern number, that gives the quantized XY conductivity. And also the semi-classical equations of motions, they're quite nice because they are very, very similar to each other. So now, since we included the Berry curvature into the semi-classical equations of motion, we also realize that we have on the one hand the Berry curvature, which is the curl of the Berry connection contributing, which is like a gauge-dependent quantity contributing to the change of the position. We also see that the magnetic field, which is the curl of the vector potential, which is also a gauge-dependent quantity, contributing to the evolution of each of the momentum. Okay, so I promised you that I wanted to explain in detail how the Chern number actually, like how it's quantized, how this is related to the XY conductivity and so on. First, like another hand-waving explanation, because I like to give hand-waving explanations. So if we have like zero magnetic field, and we consider the motion, the semi-classical motion of quasi-particles in a lattice system, then we realize if we just plug in the expression for k dot, that we have like the group velocity plus some contribution that depends on the electric field and the Berry curvature. Using this velocity, we can simply integrate over it over momentum space to get the current density, which is then proportional to the electric field itself. And if we now take the derivative of the nth component of the current density with respect to the mth component of the electric field, we see that this is identical to, so this is like the XY conductivity, and it's identical to the integral over the Berry curvature. So it gives you the nice link again between the conductivity and the Chern number. So this is a bit hand waving, and I think, to be honest, like it's also correct. I wasn't sure about a factor of 2, but actually it's like the same expression that we get for the conductivity. And like in the original paper by Theodoros and others, they considered a not so hand waving explanation for the quantized Hall conductivity. So they calculated the response using the Kubo formula, which is here a little bit small, but like it's important to note that like this whole part of the expression is in the end the Z component of the baryon connection, such that the expression that they give here exactly equals the expression that I gave one line above with a more hand waving explanation based on the semi-classical motion of the electrons. And now I like to simply compute the Chern number for a generic two-band Hamiltonian. So if we have a two-band Hamiltonian that is simply some vector d that depends on momentum times and it's like a two-dimensional system, that's also important to point out, times the vector of Pauli matrices, we can rewrite our expression for the Chern number using the baryon curvature as an integral over this vector d. And those of you who are familiar with skyrmions might recognize this expression, because this is exactly the skyrmion number. So it's also like for a magnetic system that holds magnetic skyrmions. That gives you this integer n gives you the skyrmion configurations. For example, it distinguishes if you have like a hedgehog configuration, if you don't have a hedgehog configuration. So why does it need to be an integer? Because it's related to the coverage, like how much d coverage is the unit sphere. So if we are in the trivial sector, we can now look in the left plot, we can look at the vector d as a function of kx and ky. And you see it's mostly pointing upwards. And then we can just plot the surface that is enclosed by this vector d, or covered by this vector d, if we go through all over momentum space. And you see that's like only some parts of the upper half of the sphere are covered by d. Whereas if we're in the topological sector, you see that this vector d winds around the Brillouin zone. And all of the unit sphere is in fact covered by d, and it's covered once such that we get a winding number of +1. And you can also think about other configurations, of course, where you have like where d winds in such a way that we cover this unit sphere several times, or also that winds in the opposite way, that we get a negative winding number. So this was all about Chern insulators and a little bit about the integer quantum Hall effect. But of course, there's a whole zoo of topological phases. So we have here what I introduced here, like the simple example with counterpropagating boundary modes. We have the integer quantum Hall effect, Chern insulators. But as I mentioned earlier, we can add interactions to the system to go to fractional quantum Hall effect and fractional Chern insulators. We can add time versus symmetry to the system. And this is quite important because this is like more important for realistic material realizations, such that we obtain the so-called quantum spin Hall effect, or also nowadays better known as time versus symmetric topological insulators. We can also go to higher dimensions and obtain wild semimetals. At least like this is to say, I think of wild semimetals as higher dimensional generalizations of Chern insulators. And of course, there's so much more. So there are symmetry protected topological phases related to interacting systems. Then there's topological order, and I'd like to advertise Haider's lecture starting on the 9th of March, and the same topics of current research lecture series. Then we can go to topological superconductors, and we can use like the tenfold classification of topological insulators and superconductors to find like a whole, like another zoo of topological phases, depending on the interplay of time versus symmetry and particle symmetry. We can add spatial symmetries to these systems. So for example, inversion symmetry, and get like even more phases. And using spatial symmetries, we can also generalize these wide semimetals to go to Dirac and node-aligned semimetals. And there's so much more, like for example, also topological classification of some real space defects and vortices that I didn't mention here. But for simplicity, let's just focus on one example, on the simple generalization of Chern insulators to higher dimensions on these wide semimetals. And these sound quite fancy, but actually they appear almost everywhere. So here's a plot of the band structure of iron, which is like this typical spaghetti plot along the high symmetry points of the lattice. But I'm now interested in band crossings. So if we zoom into band crossing, like this one between P and H, we can expand our Hamiltonian to around this band crossing to lowest order and momentum. So first of all, we of course get like a term that is constant in that is the same for both bands. Plus, we get the lowest order expansion in ky, plus some higher order, and so in k is plus some higher order terms in k. And this models quite well like the low energy physics around this band crossing. And I can now distinguish for, like I'm now especially interested in the first order term, and I can distinguish two different cases. And these are like I can, whenever the determinant of this matrix A is non-zero, if it's zero, then the higher order terms are important, but if it's non-zero, then the lowest order term are the most important ones. I can use the sign of this determinant to distinguish two cases, which I will distinguish by their so-called chirality, psi here, chi, sorry. And use this for a low energy description of these band crossing. And in fact, like iron and also many other common magnetic materials host these Y nodes, but they are generally far away from the Fermi energy. So although I have like a nice description of these low energy degrees of freedom, I usually don't really need them. But this is different in other materials. So first of all, let me clarify why this chi is important here. So we have the Hamiltonian, which I can now deform somehow such that I think, okay, the terms like proportional to sigma naught are not really important here because they don't change the they only change the energies itself, but not the eigenstates, and I can focus on a simple deformed Hamiltonian, which is k dot sigma, and like expand it around this vector b. And I get two different kinds of the Hamiltonian with exactly the same dispersion relation, but only distinguished by like a different chirality. And yeah, as I've mentioned before, like iron and other materials have like these Y nodes at higher energies, but so they are usually not so important. But more recently, there have been more material discoveries, like for example, tantalum arsenide that I show here, where these Y nodes occur at low energy and therefore contribute to the low energy physics of these systems, and are therefore also important for us if we care about stuff like transport properties of the samples. And these Y nodes are quite interesting because they are monopoles of Berry flux. So as I said, I can distinguish them by their chirality. So here, for example, I can just look at the chirality of +1 and get this this one Y node where I plot the Berry curvature, which is, as I introduced earlier, the curl of the barrier connection. And it always points away from these Y nodes, and with an overall sign that is determined by the chirality. So in this case, it's +1, so it points away from the Y node. But I can also think about the opposite chirality, where it points towards the Y node. And I can now just simply integrate over this Berry curvature, and I get some kind of phi, some kind of integrated flux over the surface of this monopole, and this is quantized. It's simply 2 pi times the chirality. And I have plotted here this weird blue string on top of that. So what is this supposed to be? So it's like quite an analogy to so-called Dirac string, because some of you might be familiar with magnetic monopoles, and they know that if any magnetic monopole would exist in nature, then there would be a Dirac string attached to it, where the vector potential can't be defined. And if you have like single magnetic monopole, this extends to infinity. But of course, you can also think about like having like an opposite magnetic monopole, or in this case, like an opposite monopole of Berry flux with an opposite chirality, such that the Dirac string connects these two Y nodes. And the Dirac string itself, like only its presence is necessary, but where exactly it is depends quite on the gauge choice of my system. So I can also just simply choose like a different Dirac string, because why not? But what's important here is that if I choose a certain cut through real space, which is now like a momentum space in this case, which is now a two-dimensional plane, the Dirac string either pierces this cut an even or odd number of times, and this even or odd number of times doesn't change if I change the Dirac string. So this is like some given, like the number of times the Dirac string crosses these planes, and this will be related to surface states, as we will see later. So you can also ask yourself, okay, so what is now topological for these systems? I mean, we have like some invariant, that's all fine, and so on. So how can we think about topological response functions, like similar to the quantum Hall effect, where we have like this nicely, quite exactly quantized Hall conductance? And here, the topological response is like less direct. It's the quantized circular photogalvanic effect, which counts the enclosed Berry flux. So here, this phi chi, sorry. And you can also think about like here, I only have like 2 examples where this is either +1 or -1. There are also more, like in the presence of spatial symmetries, you can also have like more like higher generalizations, so-called multifold fermions, where if you would integrate the Berry curvature over a surface surrounding this this multifold fermion node, you will realize it's like not quantized to ±2 pi, but to 2 pi times some topological charge. So in these materials, you could also measure the quantized circular photogalvanic effect. I don't have much time left, I think, because I think I'm supposed to leave a few minutes in the very end for questions, but that's not a big deal, because I think we can just continue on Wednesday also to talk about the connection to high energy physics. So let me just stress like 2 more points maybe. So one important point is that I've mentioned like the Dirac string and how it can either be cut like an even or an odd number of times. And this is related to the surface states. So let's now consider the case where we don't have only one Y node, but two Y nodes that are separated in momentum space. If I now consider like the band structure of the system as a function of kz, where z is now the direction along which I separate these Y nodes, and I look at the plane of the band crossing in momentum space, I can now think about what happens if I only consider a subsystem that I generate, like a lower dimensional subsystem, in this case a two-dimensional subsystem, that I generate by fixing a certain kz value, so by cutting it in some sense. And if I look at this particular value of kz, then I could also compute, like I could generally get a gapped system, of course, because I'm away from the Y nodes. And since it's a gapped two-dimensional system, I can do my favorite thing to do. I can calculate the Chern number, which I call C here. And for a Y semimetal, the interesting thing is that here, for example, I get a zero Chern number. But if I look at another cut separated by this band crossing by the Y node, I get a non-zero. So like here, a Chern number of 1 for my systems. So what does it mean? If I look at the three-dimensional system and have like surfaces on one direction, here it's not on the kz, like not in z direction, but either in x or y direction, then I can see surface states that only exist for a restricted range of momenta. So these are also sometimes called Fermi arcs, because here I drew them straight, these surface states visualized by these planes. But yeah, these are generally in any material resolution, they're bent. So I have Fermi arcs as a result of these different Chern numbers. And as I said before, since I don't have much time left, I'd only like to stress one more aspect, which is the chiral anomaly, which is quite important for wild semimetals. So what does it mean? So first of all, I always need to have, because of like charge conversation, as you will see in a second, I will always have like an even number of Y nodes. So the simplest case would be two Y nodes, one with positive, one with negative chirality. And due to charge conservation, the sum of the two currents of the two charges must be conserved, but the difference is not necessarily conserved. So what I can have here is that I have a so-called chiral current, so the current conservation for each left and right-handed chirality. I give the equation here at the bottom of this of the slide. So we get some contribution that is proportional to the dot product of E and B. And in the other direction, I get so-called, due to scattering, since we have a condensed matter system that is generally disordered, I get some relaxation of the two in equilibrium charges. So I have two mechanisms. One pumps me charges from one chirality to the other one, proportional to parallel magnetic and electric field. And the other ones, the other mechanism that counters it, gives some scattering. And I can think about a steady state situation, which is like highly non-equilibrium, where I'm in the following situation, where I have like a zero net current between zero net flow between the between the two different chiralities, and I pump charges from one chirality to the other, such that I have effectively a different chemic potential for the two different chiralities. And because of charge conservation, while semimetals must always host an even number of Y nodes, simply because of this chiral anomaly, right? Because if you would be able to pump charges like into one node, you must pump them from somewhere, so meaning from the other chirality. And if you think about like a condensed matter system, so here I plot like the two-dimensional Brillouin zone where I don't show the third component, Kz. I can think about these Y nodes that I can somehow create and annihilate them. So what does it mean? I can create like a pair of Y nodes at the same point in moment space. If I start from a gap system and tune some parameter that is, for example, related to some magnetization of the system, then I can move these Y nodes around and create another pair of Y nodes at a different point in momentum space, move these around, and end up in a situation where now two other Y nodes are at the same position point in momentum space, and these two Y nodes can annihilate again. So I always can only annihilate Y nodes of positive and negative chirality, and only create them in pairs of positive and negative chirality, such that I always end up with an even number of Y nodes and always the same number of plus and of minus chirality. And with that, let me quickly jump to my summary. So this is something I unfortunately didn't have time to talk about, but this is like some kind of I'm sure I will have time on Wednesday to talk about this thing, that the Y nodes are in fact surface states of a 4-dimensional quantum Hall effect, and it's very similar to the 2-dimensional quantum Hall effect. So in the 2-dimensional quantum Hall effect, you remember that we had like some surface states with a linear dispersion. These surface states were anomalous, and because of the response to an electric field, I effectively have like a quantized XY connectivity in my system. And here, in the case of the Y semimetals that I plotted above, because of the chiral anomaly that I just tried to convince you that it exists in Y semimetals, I have a current in the 4th dimension that is proportional to this E dot B term, important for the chiral anomaly, and proportional to the so-called second Chern number. And that's basically all you need to remember of this lecture. Another thing which might be relevant is the definitions of the Berry connection and the Berry curvature that help you to characterize topological systems. Okay, then thank you. And please let me know if you have any questions. Thanks. And I'm not sure if you have any questions, you can either, of course, simply unmute yourself. That might be the easiest, or you can also raise your hands. I'm sure I'm able to see you. If not,
right. Oh yeah.
Alice.
Sorry. Would you mind? Sorry, just going back to the slide where you were talking about Fermi arcs and how they come about. Would you mind just repeating how the cuts related to when we get Fermi arcs through certain planes of momentum? Sorry.
So what I mean by cut is maybe not the best expression, to be honest. What I mean by cut is that I look at so I can just treat the 3-dimensional system like I have a three-dimensional Hamiltonian, and I can treat kz not as a momentum, but as a simple as a parameter, right? Which means that if I so I can just rename it. Let's say let's call it T for now. And if I do that, I can now compute the Chern number, which I can only do for 2-dimensional systems. I can do it as a function of this parameter, right?
Yeah.
Because I'm always calculating for 2-dimensional systems. And now what I will see for such a wide semimetals is that if I vary kz, then for some values I won't get a Chern number, whereas for other values I will get like a Chern number of 1. And as a result, like I have surface states that only exist in a limited range of momenta. So here I also plotted only that's maybe should have mentioned that only plot like one of the two surfaces, right? Of course, you also have the counter propagating states of the other surface. So in this case, I get like this whole plane of surface states, like this is like where the shade gives you not only the plane, but also should give you the occupation of the states. And of course, there's also, but I didn't plot it here because it's hard to see what would happen there. You also have, of course, like on the other surface, you have like the counter-propagating surface states.
Yeah. Okay. Thank you. Yeah, that makes more sense. Cheers.
Okay. If there are no more questions, so as I said, like we will resume this lecture on Wednesday at 10 at the same time. And I think you can also use the same link that you used today. And I hope you found it interesting. And I hope next time I can convince you of some details related to high energy physics, and also can like summarize what I meant at the very end very briefly with a 4-dimensional quantum Hall effect. Thank you.